Hey, what are you up to?
Hey, I just want to play poker so bad.
Poker? I like poker too, dude. It's only us here, right? Just us
I
two?
think so. Wait, who's going to be the dealer?
Yeah, that's the problem.
And that's where Ace comes in.
Artlist.io.
Okay. All in.
All in? This guy's mad.
Bye-bye.
Wait, why did you all in? Whoa! What? That's a good poker player.
I had a pair!
Okay, so I'll explain the hardware parts of our machine ACE. So looking at here, we have 3 motors, 1 servo up here, 2 DC motors up here. The servo and the big DC motor is responsible for pushing the cars forward, for the little DC motor here to push the car outwards. The reason we have 2 DC motors is because this one has strong torque but low RPM, which means it can't spit out the card far enough. And this one has low torque but has high RPM, so it can spit out the card far enough, but struggles with pulling out the cards from all the way back here. So we decided to use both of them. And looking here, we have an LED that's connected. It's hidden under a bunch of tapes, but it's responsible for lighting up the insides of the dispenser room where we are going to use computer vision to detect the card that is under it. Now let's lift this up and see what's inside. Okay, so looking here, you see a Raspberry Pi, an Arduino Uno connected to an Adafruit Motor Shield version 1, a 12-volt battery, and hidden under here is a Raspberry Pi camera module 3, which again is responsible for the CV part. And on the lowest level we see here is another servo, same model as above, that is responsible for turning the whole body machine.
Hello everyone, my name is Justin Kim and I'll be talking about how we receive signal from our force sensitive resistors and load cells. So you can see our carpet. This is where we play our poker, and underneath there are 1 Arduino that is connected to 4 FSR, 4 load cells plus HX711, and a bunch of wires that is connected to each other. Yeah, and for our FSR, when we double tap, it's a checking, and when we press and hold, it's a folding. So if you can see, if I double tap, you'll be able to see that there are, it was able to successfully detect our double tapping. And if I press and hold, yeah, it also detects folding. And this is where the player 4 is there, sitting at, that's why it says 4 on the serial. We use 1 kilogram load cells plus HX711 to detect the number of chips that is getting on the weight scale. And this is currently 7 chips right here. If I try putting them on in the low cell number 4, it says weight 4 and 70.52. That's pretty good because our one chip weighs 10 grams, and that's because we have calibrated it that way for convenience, because it's actually 11.5 grams. And yes, that is how we connect FSR and our load cells into Arduino so that we can receive signals through Arduino and to Raspberry Pi later.
So I'll be introducing the computer vision part of our ACE machine. Our computer vision pipeline for ACE consists of 3 main stages: data collection, model training, and real-time inference. For data collection, I developed a custom capture tool that uses a Raspberry Pi camera to photograph all 52 playing cards. A key feature of this approach was ensuring that the model was trained under exactly the same environment as the deployment environment, which would essentially allow the model to optimize specifically for our deck of cards. Since we're providing players with our particular deck to play with, this intentional specialization or overfitting ensures the highest possible classification accuracy. The training phase employs a modified MobileNet v3 architecture. I replaced the classification head with a custom design featuring a 256 unit hidden layer and output layer for the 52 card classes. Our training strategy focused on achieving perfect memorization of our specific cards while incorporating enough data augmentation for lighting and orientation variance to handle a little bit of uncertainties and generalization. For real-time inference, our system captures 640 by 480 camera frames at 30 frames per second through the PyCamera 2 library. Each frame passes through the same pre-processing pipeline used during training before being fed to the model, which produces predictions in approximately 150 milliseconds. To ensure reliability, I implemented a temporal stability algorithm that requires consistent high-confidence predictions by either falling into above 90% for 1 second or 80% for 2 seconds before the model finalizes a classification. This final prediction is then sent to the game state manager. Total latency from card presentation to final classification remains under 500 milliseconds, providing smooth gameplay while maintaining 100% classification accuracy with 95% average confidence across all 52 cards.
The major challenges that we faced involved the fact that it was our first time doing many of the things that were required for doing this project. For example, the first part, we weren't very used to buying parts, so we ended up buying parts that do not really fit in our project standards and had to rebuy some of the parts. We were not used to using the RPI, so we had trouble setting it up in the first place and integrating with all the other parts. And we also were not used to 3D printing, so we had to reprint many of the parts again because of the parts not satisfying our requirement for our design. It was most these first-timer challenges that were our bottlenecks, lengthening the completion time of our project.